Hello everyone, my name is Emiliano Larach, and today I'm going to be going over lab number 2 for Flavio Fenton's Physics 2211 class at the Georgia Institute of Technology. Today we will be going over the motion of a falling object. The objective of this lab was to analyze the motion of an oatmeal cup falling from rest using Newton's second law that we can see stated right here in its velocity update version. On our first lab, the net force was 0. Now, we consider the force due to gravity and the drag force due to the atmosphere. The two forces that we are considering then will be weight, this just mass times minus the acceleration of gravity on Earth, which is 9.8 meters per second squared, and the turbulent drag force, that just minus b times velocity squared. But how do we calculate this b? This b, which is the coefficient drag, we just calculate it by adjusting the formula until the model final position matches the observed final position. Our observed value was 0.05855. The model that considered drag was closer to the observed motion, the model that just took gravity into account, overestimating the velocity of the cup. As we can see here, the model that just takes into account gravity overestimates the velocity of the cup, so it goes more distant in a less period of time, and the one that considers gravity plus drag is the one that's closer to the real motion of our cup. So this is just a quick overview of the results we will see at the end. When tracking the motion of the cup using tracker, we can see that at the end of the cup's trajectory, the distance between the center of mass of each frame is bigger, meaning the object is accelerating. As we can see in this video, at the beginning of the motion, the points are very close to each other, but when they reach the end, they start to get more separated. This means that the object is having an acceleration, and that the net force acting upon it is not zero. As I said before, if an object acceleration is changing, this means that the net force on it is not zero. We can also see this in the graph where the two initial points of the position in y times versus the time are closer than the two final points. For our gravity-only model, we consider the ball.m to be 0.76, that's just the weight of the oatmeal cup, and the initial position, we just got that from tracker. Delta t is just the regular timestamp of 0.001 seconds. In here, in the gravity-only model, we just consider weight to be our only force. Weight is just equal to minus ball m times g, and j hat, that's just the force of gravity that's going downwards. In here we have our position velocity formula, position update velocity formula, and we can see that F net is only W for this model. For the gravity and drag force, we have the same initial conditions, and the only change is now for a net force, we have the weight, the same we had before, but now we have the drag force. The drag force is just minus b times the magnitude of the velocity, because we cannot square a vector, squared, times minus j hat, because we have to remember drag goes opposite of the movement direction. And then we have our velocity update formula, accounting for net force, we have drag force too. The observed trajectory and the predicted model that accounts for drag and gravity are the closer ones. The predicted model without drag force overestimates the displacement, as we can see here. This is because the gravity plus drag, which is yellow, better accounts for our real conditions. That of course include the effect of drag force. But which model predicts the terminal velocity? The terminal velocity is when F net equals 0. Drag force and gravity force cancel each other. In this case, it will be our second model, the one that takes into account drag force. If the trajectory was longer, because we need time to reach that terminal point, the model that takes gravity and drag force into account will predict this terminal velocity. But now imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the object was initially dropped from rest? We know that velocity is proportional to drag, so the terminal velocity would be exactly the same. We would just take more time to reach this velocity. As we can see here in our gravity and drag force model, we can see that the drag force as the velocity goes faster because the object is accelerating because of the gravity force, we can see that the drag force, which is this vector here, is also growing from 0.28 to 0.29. As a conclusion, The model accounting for drag force and weight force due to gravity was the most accurate representation of the oatmeal cup's motion. It doesn't matter if an object has an initial velocity, because drag is proportional to velocity. The object's terminal velocity will remain the same. The areas I would like to improve for my next lab are just the video recording and the tracker scaling. I hope these conclusions better help you understand this lab experiment, and I hope to see you guys in my next lab. Thank you very much.